Deep in the heart of our solar system, something is moving toward us that shouldn't exist. An object from another star system, older than our Sun, is behaving in ways that challenge everything we thought we knew about comets. It's releasing the wrong gases, pointing its tail in the impossible direction, and following a trajectory so perfectly timed that some scientists are wondering if it was designed. This is 3I Atlas, and its strange behaviour is keeping astronomers awake at night. Hello and welcome back to Cosmic Perspectives. I'm genuinely thrilled you're here, whether you're settling in for the evening, taking a quiet break from your day, or simply letting your curiosity guide you into the mysteries of our universe. Tonight, we're embarking on a journey that will take us beyond the familiar boundaries of our solar system to examine something truly extraordinary, something that has the astronomical community both excited and deeply puzzled. Before we begin, I'd love to know where in the world you're joining me from tonight. Are you watching from a bustling city where the stars are hidden by light pollution, or perhaps from somewhere remote where the Milky Way stretches across your sky? Drop a comment and let me know your location and what time it is where you are. There's something wonderfully humbling about knowing that people from across our planet are gathering to contemplate the same cosmic mysteries. And if you find yourself drawn to these explorations of the universe's deeper questions, if you enjoy having your mind gently stretched by the implications of what we're discovering out there in the dark, consider subscribing. It helps more curious minds find their way to these conversations, and honestly, we could use more people willing to sit quietly with the big questions. Let me paint you a picture of July 1st, 2025, at the Rio Hurtado station in Chile, part of the Atlas Asteroid Survey System. Computers were processing the night's observations when something unusual appeared in the data. At first glance, it looked like just another asteroid, a small rocky body drifting through space. But as astronomers traced its path backward through time, something remarkable became clear. This object hadn't originated from the asteroid belt between Mars and Jupiter, or from the distant Kuiper belt beyond Neptune. It had come from somewhere else entirely, somewhere unimaginably far away. This was 3I Atlas, and it carried with it the distinction of being only the third confirmed visitor from beyond our solar system in all of recorded human history. Think about that for a moment. In the entire span of human civilization, from the first time our ancestors looked up at the night sky and wondered what those points of light might be, we have definitively identified only 3 objects that originated from other star systems and travelled the vast emptiness of interstellar space to visit us here. The discovery itself tells a fascinating story of cosmic hide and seek. For weeks leading up to its official identification, 3I Atlas had been hiding in plain sight, camouflaged against the dense star fields of our galaxy's centre. Imagine trying to spot a single firefly against the backdrop of Times Square at midnight, and you begin to understand the challenge. It wasn't until the comet had moved away from this stellar confusion that astronomers could clearly discern its path and recognise it for what it was. But here's where the story takes its first strange turn. When researchers began calculating the object's trajectory with precision, they discovered something that made them pause and double-check their mathematics. 3I Atlas wasn't just passing through our solar system on any random path. It was travelling along the same plane, the same flat disk, where most of our planets orbit the Sun. Now space is three-dimensional, vast beyond comprehension. An object approaching from interstellar space could arrive from literally any direction, up, down, sideways, at any conceivable angle. the chance of it naturally aligning with our solar system's orbital plane is roughly 1 in 500. Those aren't impossible odds, but they're certainly eyebrow-raising ones. Harvard astronomer Avi Loeb, never one to shy away from provocative questions, put it succinctly when he noted that this alignment raises the question of whether this trajectory was designed. Now, before you start imagining alien spacecraft, let's be clear about what Loeb is suggesting. He's not claiming definitive proof of artificial origin, but rather pointing out that when we encounter statistical improbabilities in nature, it's worth asking whether there might be more to the story than pure chance. The trajectory becomes even more intriguing when you consider the timing. Atlas isn't just aligned with our planetary plane, it's arriving at precisely the right moment to have close encounters with Mars, Venus and Jupiter. If you were an advanced civilization looking to explore a star system, you might design a probe to follow exactly this kind of path, one that would allow you to study multiple worlds during a single flyby. As astronomers continued their observations throughout the summer of 2025, more peculiarities emerged. Atlas was moving fast, incredibly fast. At 245,000 kilometers per hour relative to our solar system, it became the fastest object ever detected within our cosmic neighborhood. To put that speed in perspective, it's moving so quickly that it could travel from New York to Los Angeles in about 37 seconds. This velocity tells us something profound about the object's journey. Unlike comets born in our solar system, which are gravitationally bound to the Sun and follow predictable elliptical orbits, 3i Atlas is on what astronomers call a hyperbolic trajectory. Its path is open-ended, like a branch of a hyperbola that extends to infinity. It came from the depths of interstellar space, and after its brief visit to our solar system, it will return to those depths, never to come back. The mathematical signature of this trajectory is encoded in a number called orbital eccentricity. Any object with an eccentricity greater than 1 is unbound from our Sun's gravitational influence. 3i Atlas has an eccentricity of 6.2, meaning it's not just unbound, it's dramatically, emphatically unbound. For comparison, the first interstellar visitor, Oumuamua, had an eccentricity of about 1.2, barely escaping our solar system. The second visitor, comet Borisov, came in at 3.6.3i Atlas, massively outpaces both, carrying with it clear evidence of a journey that began light years away. But speed and trajectory were just the beginning of 3i Atlas's mysteries. As telescopes around the world turned their attention to this interstellar traveller, they began to notice something puzzling about its size. Early estimates suggested the object could be enormous, perhaps up to 20 kilometers across. If true, this would make it a substantial mountain of rock and ice, hurtling through space at phenomenal speed. However, as more sophisticated observations came in, the size estimates became wildly contradictory. The Hubble Space Telescope, with its exquisite resolution, suggested a much smaller object, perhaps less than a kilometre in diameter, but then other instruments detected signals that implied something much larger, potentially 46 kilometres across, making it 1,000,000 times more massive than the previous interstellar comet Borisov. These conflicting measurements reveal something important about the challenges of studying objects from other star systems. 3i Atlas is surrounded by a cloud of gas and dust called a coma, which forms as the comet's icy surface sublimates in the warmth of our Sun. This coma can obscure the true size of the nucleus, the solid core of the comet, making accurate measurements incredibly difficult. It's like trying to measure the size of a streetlight while looking through dense fog. In August 2025, NASA's James Webb Space Telescope turned its infrared eyes toward 3I Atlas, and what it discovered was nothing short of revolutionary. The chemical composition of this interstellar visitor was unlike anything astronomers had seen before. Most comets in our solar system are often described as dirty snowballs, chunks of water ice mixed with rock and organic compounds. When they approach the sun, water vapor dominates the gases they release, creating the characteristic bright coma and tail we associate with comets. But 3I Atlas was different, profoundly different. Instead of water vapor, the Webb telescope detected an atmosphere around 3I Atlas that was absolutely dominated by carbon dioxide. The comet was releasing about 70 kilograms of carbon dioxide every second, while water production was barely detectable, perhaps 4.5 kilograms per second at most. This represents one of the highest carbon dioxide to water ratios ever recorded in a comet, a chemical signature that suggests 3I Atlas formed under very different conditions than the comets native to our solar system. Think about what this means. The chemistry of a comet is like a fingerprint, a record of the conditions that existed in the disk of gas and dust around a young star where it formed billions of years ago. The overwhelming presence of carbon dioxide in 3I Atlas tells us that its birthplace was remarkably different from the early solar nebula that gave rise to our own comets. Perhaps it formed closer to its parent star, where only the most volatile compounds could condense into solid form. Or maybe it was exposed to higher levels of radiation that transformed its chemical composition over eons of interstellar travel. But the chemical mysteries didn't end with carbon dioxide. Ground-based telescopes detected even more unusual emissions from 3I Atlas. The Very Large Telescope in Chile identified the spectral signatures of cyanide gas and, most surprisingly, atomic nickel vapor. The presence of nickel is particularly intriguing because it's extremely rare in the atmospheres of solar system comets. By August 2025, 3I Atlas was releasing nearly 5 grams of nickel and 18 grams of cyanide every second, and these emission rates were increasing rapidly as the comet approached the sun. The detection of these exotic gases raises profound questions about the environment where 3I Atlas originated. Nickel emission in comets is thought to be linked to specific chemical processes involving carbon-bearing molecules, possibly indicating that this interstellar visitor formed in a region rich in heavy elements and complex chemistry. Perhaps the most visually striking anomaly of 3I Atlas is something that seems to violate one of the most basic rules of cometary behaviour. When the Vera Rubin Observatory captured high-resolution images of the comet in early July 2025, astronomers were stunned to see something that shouldn't exist: a tail pointing toward the sun. Every schoolchild learns that comet tails always point away from the sun, pushed outward by the solar wind and radiation pressure. This is such a fundamental aspect of cometary physics that it's often used to determine the direction to the sun in images of the solar system. But 3I Atlas was breaking this rule, sporting what appeared to be a dusty tail stretching directly toward our star. The implications of this observation are profound and puzzling. For a tail to point sunward, the comet must be ejecting material with enough momentum to overcome the outward push of solar radiation. This suggests that 3I Atlas is releasing massive particles, chunks of dust and debris too heavy to be blown away by the solar wind. The material continues forward along the comet's trajectory, creating the illusion of a tail pointing in the wrong direction. While this phenomenon has been observed before in a few distant comets, it's extremely rare and poorly understood. The fact that 3I Atlas, an object from another star system, is displaying this behaviour adds another layer of mystery to its already enigmatic nature. What kind of internal processes could be driving such unusual material ejection? Is this related to its strange chemical composition, or is it evidence of some other exotic property of interstellar comets? The sunward tail of 3I Atlas serves as a visible reminder that this visitor from the depths of space doesn't play by the rules we've come to expect from objects in our solar system. It's as if the comet is actively defying our understanding of cometary physics, forcing astronomers to reconsider fundamental assumptions about how these objects behave. As we delve deeper into the mysteries of 3I Atlas, we're beginning to realise that this interstellar visitor might be more than just an unusual comet. Its perfect trajectory, bizarre chemistry, and rule-breaking behaviour have some scientists wondering if we're dealing with something unprecedented in the history of astronomy. But to understand the full implications of these discoveries, we need to explore the most controversial question surrounding 3I Atlas. Could this ancient traveller be something other than a natural object? The story of 3I Atlas is far from over, and the answers we seek may challenge everything we think we know about our place in the cosmic order. But perhaps the most mind-bending aspect of 3I Atlas isn't what it's doing now, but when it began its journey. As astronomers traced the comet's path backward through space and time, they made a discovery that sent ripples of excitement through the scientific community. This visitor from the stars might be older than our entire solar system. Kinematic studies which track the motion of objects through our galaxy suggest that 3I Atlas originated in what astronomers call the thick disk of the Milky Way. This is a region populated by some of the most ancient stars in our galaxy, stellar relics from when the universe was young, and the heavy elements we take for granted were still rare and precious. If these calculations are correct, 3I Atlas could be as much as 7 billion years old, making it 3 billion years older than the Sun itself. Let that sink in for a moment. While our solar system was still nothing more than a cold, dark cloud of gas and dust drifting through space, 3I Atlas may have already been a fully formed comet, orbiting some distant star in the early galaxy. It witnessed the birth of countless stellar generations, survived the violent death throes of massive stars, and somehow found itself ejected into the void between the stars, beginning a journey that would last billions of years. This ancient pedigree makes 3I Atlas more than just a scientific curiosity. It's a time capsule, a pristine sample of matter from the early universe, preserved in the deep freeze of interstellar space. The chemical signatures we're detecting today, that unusual carbon dioxide dominance and exotic nickel emissions, might be telling us about conditions that existed when our galaxy was fundamentally different from what we see today. Think about the implications of studying something so ancient. Every measurement we take, every spectrum we analyse, is potentially giving us insight into stellar environments that existed when the universe was less than half its current age. In a very real sense, 3I Atlas is allowing us to reach back through time and touch the primordial galaxy. As observations of 3I Atlas continued through the late summer of 2025, another peculiarity emerged that has astronomers scratching their heads. This interstellar visitor appears to be remarkably dry, at least by cometary standards. Water is the most abundant volatile compound in most comets we've studied. It's what creates those spectacular tails and comas that make comets such beautiful objects to observe. When a comet approaches the Sun, water ice sublimates directly from solid to gas, carrying with it dust and other materials to create the characteristic fuzzy appearance that distinguishes comets from asteroids. But 3I Atlas seems to have missed that memo. Despite being well within the region of our solar system where water ice should be actively sublimating, the comet is producing water vapour at barely detectable levels. The Swift Observatory managed to detect hydroxyl emissions, which serve as a proxy for water production, but the rates were surprisingly low, especially when compared to the torrents of carbon dioxide streaming from the comet's nucleus. This water scarcity is more than just an observational curiosity. It tells us something fundamental about the environment where 3I Atlas formed. In our solar system, water is abundant because our early solar nebula existed at just the right distance from the young sun for water to condense into ice. But the star system that gave birth to 3I Atlas must have been very different. Perhaps it formed in a region where water was scarce, or where the intense radiation from a massive nearby star prevented water ice from accumulating. Or maybe the billions of years of exposure to cosmic rays during its interstellar journey have somehow altered its composition, breaking down water molecules and leaving behind the carbon-rich chemistry we observe today. The water mystery deepens when we consider that 3I Atlas is clearly an active comet. It has a substantial coma, it's releasing gases at significant rates, and it even has that puzzling sunward-pointing tail. All of this activity suggests that the comet's nucleus contains volatile materials that are responding to solar heating. But if it's not water driving this activity, what is? The answer seems to be carbon dioxide, but this raises even more questions. Carbon dioxide ice is less stable than water ice, meaning it should sublimate more readily. For 3I Atlas to still be rich in carbon dioxide after potentially billions of years in space suggests that its nucleus might be much larger than we initially thought, with vast reservoirs of CO2 ice protected beneath an insulating layer of dust and rock. As autumn approached in 2025, astronomers around the world found themselves in a race against time and celestial mechanics. 3I Atlas was approaching its closest point to the Sun, its perihelion, scheduled for October 29th. This would be the moment of peak activity, when the comet would be at its warmest and most volatile, potentially revealing new aspects of its mysterious nature. But there was a cruel twist of cosmic geometry at play. Due to the alignment of Earth and 3I Atlas relative to the Sun, the comet would be hidden behind our star during its most interesting phase. From Earth's perspective, it would be lost in the Sun's glare, invisible to our most powerful telescopes precisely when it might be undergoing its most dramatic changes. This created an urgent window of opportunity that was rapidly closing. Every clear night became precious, every observation potentially the last chance to gather crucial data before 3I Atlas disappeared behind the solar disk. Telescopes around the world worked in coordination, from ground-based observatories to space-based platforms, all focused on extracting every possible bit of information from this fleeting visitor. The Hubble Space Telescope captured some of the highest resolution images ever taken of an interstellar object, revealing details of the comet's coma and the subtle structures within it. The James Webb Space Telescope continued its spectroscopic analysis, tracking how the chemical composition evolved as 3I Atlas warmed in the increasing solar radiation. Ground-based facilities monitored the exotic emissions of nickel and cyanide, documenting their rapid increase as the comet approached perihelion. But perhaps most intriguingly, mission planners began discussing the possibility of spacecraft observations during the solar occultation period. While Earth-based telescopes would be blind to 3R Atlas during its closest approach, spacecraft positioned elsewhere in the solar system might still have clear lines of sight to the comet. The European Space Agency's Solar Orbiter mission, designed to study the Sun from various angles, found itself in a unique position to potentially observe 3I Atlas during its perihelion passage. The Parker Solar Probe, humanity's fastest spacecraft and closest solar explorer, might also catch glimpses of the interstellar visitor as it navigated the inner solar system. These potential observations carried enormous scientific value. Perihelion passage is often when comets undergo their most dramatic changes. They can fragment, revealing their internal structure, or experience massive outbursts of activity that shed light on their composition and history. For 3I Atlas, with all its mysterious properties, the perihelion passage might finally provide answers to some of the questions that have been puzzling astronomers. As the unusual properties of 3I Atlas continue to accumulate, a small but vocal group of scientists began asking an extraordinary question. Could this interstellar visitor be artificial? The suggestion came primarily from Harvard astronomer Avi Loeb, who has made a career of asking uncomfortable questions about unusual objects from space. Loeb developed what he calls the Loeb scale, a ranking system from 0 to 10, where 0 represents a definitely natural object and 10 implies a definitely artificial one. He currently ranks 3I Atlas as a 4, acknowledging that it's most likely natural, but noting that its collection of anomalous properties deserves serious consideration. The case for artificial origin, while speculative, rests on several compelling observations. First, there's that statistically improbable trajectory, perfectly aligned with our solar system's orbital plane and timed for close encounters with multiple planets. If you were designing a probe to study our solar system, you might choose exactly this path. Then there's the unusual composition, the dominance of carbon dioxide over water, the exotic emissions of nickel and cyanide, and the apparent age of the object all suggest formation conditions very different from anything we see in our local cosmic neighbourhood. Could these be signatures of artificial materials or propulsion systems we don't recognise? The sunward-pointing tail adds another layer of intrigue. While this phenomenon has been observed in a few natural comets, it could also be consistent with directed material ejection, perhaps from some kind of propulsion or guidance system. The massive particles being ejected might not be random debris, but deliberately released materials. Most provocatively, Loeb suggests that the timing of 3I Atlas's arrival might not be coincidental. The comet's trajectory would allow a hypothetical mothership to release smaller probes that could reach Earth, Mars, and Venus as these planets move into the paths of the mini-probes. It's a scenario straight out of science fiction, but one that's at least theoretically possible given the object's unusual orbital characteristics. The scientific community's reaction to these suggestions has been mixed, to put it mildly. Most astronomers firmly believe that 3I Atlas is a natural object, albeit an unusual one. They argue that the universe is vast and ancient, containing environments and processes we've never encountered before. The strange properties of 3I Atlas might simply reflect the exotic conditions that exist around other stars, not evidence of alien technology. Chris Lintott, an astronomer at Oxford University, dismissed the artificial origin hypothesis as nonsense on stilts, arguing that it diminishes the genuine scientific excitement surrounding this remarkable interstellar visitor. The majority of the astronomical community shares this view, seeing 3i Atlas as a natural phenomenon that's teaching us about the diversity of objects in our galaxy. But Loeb's questions serve an important purpose, even if his conclusions are controversial. Science advances by challenging assumptions and considering possibilities that might seem unlikely. While the artificial origin hypothesis remains a long shot, the act of seriously considering it forces us to think more carefully about what we expect from natural objects and what might constitute evidence of something else. As Loeb himself acknowledges, the most likely outcome will be that 3i Atlas proves to be a completely natural, if unusual, interstellar comet. But the process of ruling out alternatives, of gathering data and testing hypotheses is how we deepen our understanding of the universe and our place within it. As 3i Atlas disappeared behind the Sun in late October 2025, the astronomical community settled in for a waiting game. The comet would remain hidden from Earth-based observation for several weeks, undergoing its closest approach to our star in the privacy of solar glare. When it emerged in early December, it would be a changed object, potentially bearing the scars or enhancements of its intimate encounter with solar radiation. The post-perihelion observations promised to be just as revealing as everything that came before. Comets often fragment during their closest approach to the Sun, and if 3i Atlas breaks apart, it could reveal the internal structure and composition that have remained hidden beneath its dusty exterior. Even if it survives intact, the intense heating might have altered its surface, exposing fresh materials and changing its chemical emissions. Hubble Space Telescope observations scheduled for November and December will search for new molecular signatures, looking for hydroxide and hydrogen that might provide additional clues about the comet's composition. The James Webb Space Telescope will continue its spectroscopic analysis, tracking how the chemical fingerprint of this interstellar visitor evolves as it begins its journey back to the outer solar system. But perhaps most importantly, the observations of 3i Atlas are changing how we think about interstellar objects in general. With only 3 confirmed visitors from other star systems, each new arrival dramatically expands our understanding of what's possible. Oumuamua showed us that interstellar objects exist and can have unusual properties. Comet Borisov demonstrated that some visitors behave much like objects from our own solar system. And now 3i Atlas is revealing that the diversity of interstellar objects might be far greater than we ever imagined. The strange behaviour of 3i Atlas is forcing astronomers to develop new models and theories about how comets form around other stars, how they survive the journey through interstellar space, and what they can tell us about conditions in distant planetary systems. Every measurement, every spectrum, every image is a piece of data about environments that exist light years away, places we may never visit, but can study through the messengers they occasionally send our way. As we continue to monitor 3i Atlas and await its reappearance from behind the Sun, we're reminded of how much we still don't know about our cosmic neighbourhood. The universe continues to surprise us, to challenge our assumptions, and to reveal new mysteries just when we think we're beginning to understand the rules. Whether 3i Atlas proves to be a natural comet with exotic properties, or something more unusual, its visit has already enriched our understanding of the galaxy we inhabit. It's shown us that the space between the stars isn't empty, but filled with ancient travellers carrying stories of distant worlds and distant times. And perhaps most wonderfully, it's reminded us that we live in a universe where the impossible can become possible, where objects older than our solar system can arrive unannounced at our cosmic doorstep, bringing with them questions we never thought to ask and answers we're still learning to understand. The journey of 3I Atlas through our solar system is nearing its end, but the questions it has raised will keep scientists busy for years to come. And as we've learnt from studying the quantum realm, sometimes the most profound mysteries exist not in distant galaxies, but in the fundamental nature of reality itself. Speaking of which, there's another scientific mystery that's been keeping physicists awake at night, one that challenges our understanding of existence in ways that make 3I Atlas look straightforward by comparison. It's a phenomenon so bizarre, so fundamentally unsettling, that many scientists wish they could simply ignore it. But they can't, because it's built into the very fabric of reality itself. I'm talking about the quantum measurement problem, and why it's causing some of the world's brightest minds to question whether our universe is even real. That's exactly what we'll be exploring next time in The Quantum Paradox, Terrifying Scientists, and They Can't Explain It. Thank you for joining me on this journey to the edges of our solar system and the boundaries of our understanding. Until next time, keep looking up, keep questioning, and remember that in a universe as vast and strange as ours, the most extraordinary discoveries often come from the most unexpected places. As we watch 3I Atlas continue its ancient journey through our solar system, there's another piece of this cosmic puzzle that deserves our attention. Peter Veres, a Harvard astronomer who works at the Minor Planet Center, has proposed what might be the most elegant explanation yet for some of the comet's unusual behavior. Imagine, if you will, an object drifting through the absolute cold and darkness of interstellar space for billions of years. During this unimaginably long journey, it's constantly bombarded by cosmic rays, high-energy particles that stream through the galaxy at nearly the speed of light. These cosmic rays don't just bounce off the surface, they penetrate deep into the material, breaking apart molecules and rearranging atoms in ways we're only beginning to understand. Veres suggests that this prolonged exposure to cosmic radiation might have created something like a protective shell around 3I Atlas, a hardened crust baked by billions of years of particle bombardment. This crust could explain why the comet initially appeared to lack the typical features we associate with active comets. The surface might have been sealed, preventing the volatile materials beneath from escaping into space. But here's where the theory becomes truly fascinating. As 3I Atlas approaches our sun and begins to warm, this ancient crust might start to crack and peel away, like old paint flaking off a weathered barn. Suddenly, pristine materials that have been locked away since the comet's formation would be exposed to sunlight for the first time in eons. The result would be a dramatic increase in activity, exactly what astronomers have been observing as the comet draws closer to perihelion. This crust theory offers a beautiful explanation for many of 3I Atlas's peculiarities. The unusual chemical composition might not be evidence of exotic formation conditions, but rather the signature of materials that have been processed by cosmic rays over geological timescales. The delayed onset of cometary activity, the strange emissions, even the sunward-pointing tail, could all be consequences of this gradual awakening as the ancient surface gives way to reveal the comet's true nature. There's something almost poetic about this idea. I Atlas becomes not just a visitor from another star system, but a time capsule slowly opening, revealing layer by layer the story of its billion-year journey through the void. Each crack in its protective shell, each puff of gas released into space, is like turning the page of a book written in the language of atoms and molecules. To truly appreciate the significance of 3I Atlas, we need to step back and consider the vast scale of our galaxy and the rarity of interstellar encounters. The Milky Way contains somewhere between 200 and 400 billion stars, each potentially surrounded by its own family of planets, asteroids, and comets. The distances between these stellar systems are so enormous that they strain the limits of human comprehension. Our nearest stellar neighbour, Proxima Centauri, lies about 4.2 light-years away. That might not sound like much until you realise that it represents roughly 25 trillion miles. If you could somehow travel at the speed of our fastest spacecraft, it would take you about 70,000 years to make the journey, and that's just to the closest star. Against this backdrop of cosmic isolation, the arrival of 3I Atlas becomes truly extraordinary. This object has somehow escaped from its birth system, survived a journey of potentially millions of years through the near-perfect vacuum of interstellar space, and arrived at our cosmic doorstep, carrying with it physical evidence of another world. The mechanics of how objects like 3I Atlas become interstellar wanderers are still not fully understood. Most likely, gravitational interactions with massive planets or close encounters with other stars can provide enough energy to accelerate comets beyond their system's escape velocity. Once free, these objects begin epic journeys through the galaxy, most destined never to encounter another star system. But occasionally, purely by chance, one of these cosmic nomads crosses paths with our solar system. The gravity of our sun bends their trajectory, sometimes capturing them temporarily before flinging them back into the void. For a brief moment in cosmic time, we become connected to another star system through this physical messenger. Consider the profound implications of this connection. The atoms that make up 3I Atlas were forged in the nuclear furnaces of stars that lived and died billions of years ago. They were incorporated into a disk of gas and dust around a young star, condensed into solid form in the cold outer reaches of that distant system, and then began a journey that spanned a significant fraction of our galaxy's age. Now, through the marvels of modern astronomy, we're able to study these alien atoms, to decipher their chemical signatures, and to piece together the story of their origin. In a very real sense, we're conducting archaeology on a galactic scale, using the tools of spectroscopy and orbital mechanics to explore the ancient history of our stellar neighbourhood. The story of 3I Atlas is also a testament to the incredible sophistication of modern astronomical technology. The discovery itself was made possible by the Atlas system, a network of robotic telescopes designed to scan the entire visible sky every few nights, looking for objects that move or change brightness. These automated surveys represent a revolution in astronomy. Rather than relying on human observers to peer through eyepieces and manually track celestial objects, we now have robot sentinels that never sleep, never get tired, and never miss a clear night. They capture millions of images, process them through sophisticated algorithms, and flag anything that appears unusual for human follow-up. The detection of 3I Atlas required this image to be compared with previous observations of the same patch of sky, revealing the telltale motion that distinguished it from the background stars. But identifying motion is just the first step. Determining that this motion represents an interstellar trajectory requires precise measurements of position over time and complex orbital calculations. This is where the global network of professional and amateur astronomers comes into play. Within hours of the initial discovery, telescopes around the world were pointed at 3I Atlas, gathering the precise positional measurements needed to calculate its orbit. The Minor Planet Center, which serves as the global clearinghouse for asteroid and comet discoveries, coordinated these observations and performed the calculations that revealed the object's interstellar origin. But position and velocity are just the beginning of what modern telescopes can tell us about objects like 3 Atlas. Spectroscopy, the analysis of light broken down into its component colours, allows us to identify the chemical composition of objects millions of miles away. When atoms and molecules in the comet's coma absorb or emit light at specific wavelengths, they create unique fingerprints that can be read by spectrographs attached to large telescopes. The James Webb Space Telescope, with its unprecedented sensitivity in the infrared portion of the spectrum, can detect the thermal emission from molecules that would be invisible to optical telescopes. This capability was crucial for identifying the carbon dioxide dominance in 3I Atlas's coma and for discovering the exotic molecular species that make this comet so unusual. High-resolution imaging from telescopes like Hubble allows astronomers to study the detailed structure of the coma and tail, revealing features like the mysterious sunward-pointing dust trail that has puzzled observers. These images can be processed and enhanced to bring out subtle details that might otherwise be lost in the glare of the comet's overall brightness. The discovery of 3I Atlas raises an obvious question. How many other interstellar objects are out there, waiting to be discovered? Current estimates suggest that at any given time, there might be thousands of interstellar objects passing through our solar system, most too small or too dark to detect with current technology. The Vera Rubin Observatory, currently under construction in Chile, promises to revolutionize our ability to find these cosmic visitors. Once operational, it will survey the entire visible sky every few nights with unprecedented depth and precision, potentially discovering interstellar objects at a rate of several per year. This dramatic increase in discovery rate will transform our understanding of interstellar populations. Instead of having just 3 examples to study, we might soon have dozens or even hundreds. This statistical sample will allow astronomers to determine whether objects like 3I Atlas are typical of interstellar comets or represent rare and unusual cases. The European Space Agency's upcoming Comet Interceptor mission adds another dimension to interstellar object research. This spacecraft will wait in orbit until a suitable target is identified, then quickly maneuver to intercept and study it up close. While originally designed for comets from our own solar system, the mission could potentially be redirected to study an interstellar visitor if one arrives at the right time and place. The prospect of spacecraft missions to interstellar objects opens up extraordinary possibilities. Instead of studying these visitors from hundreds of millions of miles away, we could potentially send probes to sample their composition directly, to study their internal structure, and to search for organic compounds that might tell us about the chemistry of other star systems. Such missions would be technically challenging, requiring spacecraft capable of matching the high velocities of interstellar objects and operating far from the Sun, where solar power becomes impractical. But the scientific rewards would be immense, providing ground truth data to calibrate our remote observations and potentially revealing aspects of interstellar object composition that can't be detected from Earth. As we contemplate the journey of 3I Atlas through our solar system, we're confronted with questions that extend far beyond astronomy and into the realm of philosophy. What does it mean for our understanding of our place in the universe to know that we're regularly visited by objects from other star systems? For most of human history, our solar system seemed like an isolated island in the cosmic ocean. The stars were distant points of light, beautiful but unreachable, existing in a realm completely separate from our earthly experience. The planets, moons, asteroids, and comets of our own system represented the full extent of the physical universe we could hope to study and understand. But the discovery of interstellar objects like 3I Atlas fundamentally changes this perspective. We're not isolated, after all. The galaxy is a connected network of stellar systems linked by the occasional exchange of physical matter. The comet currently warming in the light of our sun carries within its ancient ice the actual atoms of another star system, making us temporary custodians of truly alien material. This connection operates on timescales that dwarf human experience. The journey of 3I Atlas from its birth system to our solar system likely took millions or even billions of years. During that time, entire species have evolved and gone extinct on Earth. Continents have drifted across our planet's surface. Our sun has completed dozens of orbits around the galactic centre. Yet through all of this change, 3I Atlas has been steadily approaching, carrying its cargo of ancient ice and rock across the vast emptiness between the stars. There's something humbling about this perspective. Our individual lives, our civilizations, even our species, exist as brief moments in the epic journey of objects like 3I Atlas. Messenger arrives, giving us a fleeting opportunity. We happen to be present at the moment when this particular to study a piece of the ancient galaxy before it continues on its eternal voyage. The chemical composition of 3I Atlas also carries philosophical weight. The unusual dominance of carbon dioxide over water suggests that the conditions around other stars can be dramatically different from what we experience in our own system. This diversity of environments implies a corresponding diversity of outcomes, different paths that planetary system formation can take, different chemical legacies that can be preserved in cometary nuclei. If we extrapolate from the small sample of interstellar objects we've studied so far, it seems likely that the galaxy contains a vast menagerie of different types of comets, asteroids, and possibly other objects we haven't yet imagined. Each stellar system might produce its own unique population of small bodies shaped by the particular conditions that existed during their formation billions of years ago. As 3I Atlas completes its passage through our solar system and begins its journey back to interstellar space, we can't help but wonder about its ultimate fate. Unlike comets native to our system, which follow predictable elliptical orbits that bring them back to the inner solar system, every few decades or centuries, 3I Atlas is on a one-way trip. Its hyperbolic trajectory will carry it away from the Sun at ever-increasing distance, eventually reaching the heliopause, the boundary where our Sun's influence gives way to the interstellar medium. Beyond that point, it will once again become a wanderer in the void, its brief encounter with our star system nothing more than a momentary interruption in an eternal journey. But this journey won't be entirely solitary. As 3I Atlas travels through interstellar space, it will slowly approach other star systems, though none are likely to capture it as dramatically as our Sun has done. Over millions of years, it might pass within a few light years of dozens of different stars, each encounter providing a slight gravitational nudge that alters its trajectory. Eventually, after eons of wandering, 3I Atlas might find itself approaching another planetary system, perhaps around a star that doesn't yet exist, formed from gas and dust that is currently floating freely in space. When that distant encounter occurs, billions of years in the future, The comet will carry with it not only the chemical signature of its birth system, but also subtle traces of its visit to our solar system. The water molecules it picked up from our sun's solar wind, the cosmic ray damage accumulated during its passage through our heliosphere, even the microscopic impacts from interplanetary dust will all be part of its cargo as it approaches that future star. In a sense, 3i Atlas becomes a messenger, not just from its original home, but from every system it has visited along the way. This continuity across cosmic time creates a network of connections between stellar systems that operates on scales almost too vast to comprehend. Matter flows through the galaxy not just in the form of gas and dust, but as discrete objects carrying the physical and chemical history of their journeys. Each interstellar visitor is both an ending and a beginning, the conclusion of one story and the start of another. When we consider the age of 3i Atlas, potentially billions of years older than our solar system, we realize that it has already lived through multiple cycles of this cosmic exchange. It may have visited other star systems before arriving at ours, each encounter leaving subtle traces in its composition and structure. The object we're studying today is not just a sample of one alien world, but potentially a composite record of multiple stellar environments. The study of 3i Atlas represents just the beginning of a new era in astronomy. As our detection capabilities improve and more interstellar objects are discovered, we'll begin to build a comprehensive picture of the different types of materials that exist in our galactic neighborhood. Each new visitor will add another piece to this cosmic puzzle, revealing the diversity of environments and processes that shape matter in other star systems. The upcoming decade promises to be particularly exciting for interstellar object research. The Vera Rubin Observatory will begin operations, dramatically increasing the discovery rate of these rare visitors. The James Webb Space Telescope will continue to provide unprecedented detail about their chemical composition. New spacecraft missions may launch to intercept and study them directly, but perhaps most importantly, the discovery of objects like 3i Atlas is changing how we think about our relationship with the rest of the galaxy. We're not isolated observers studying distant stars through telescopes. We're participants in a vast, slow-motion exchange of matter that connects every stellar system in our cosmic neighborhood. This realization comes at a time when humanity is beginning to take its first tentative steps beyond Earth, establishing permanent presence in space and planning missions to other worlds in our solar system. The knowledge that we're regularly visited by materials from other star systems adds a new dimension to these endeavors. We're not just exploring our local cosmic environment, we're studying samples of the broader galaxy that deliver themselves to our doorstep. The techniques we develop to analyze interstellar objects will also prove valuable for understanding the materials we encounter as we explore other worlds. The spectroscopic methods used to identify exotic molecules in 3i Atlas's coma will help us search for signs of past or present life on Mars, Europa, and Enceladus. The orbital dynamics calculations that revealed its interstellar origin will guide our navigation to asteroids, comets, and eventually other star systems. In a very real sense, objects like 3i Atlas are preparing us for our eventual expansion beyond the solar system. They're showing us what we might expect to find in the interstellar medium, teaching us about the chemistry and physics of materials that have spent eons in the void between the stars. When human explorers finally venture beyond the heliopause, they'll be travelling through a medium that's not empty but filled with ancient wanderers like 3i Atlas each carrying its own story of cosmic evolution. The strange behaviour of 3I Atlas, its unusual chemistry and mysterious properties, reminds us that the universe still holds countless surprises. Despite centuries of astronomical observation and decades of space exploration, we're still encountering phenomena that challenge our understanding and force us to expand our theories. This is perhaps the most exciting aspect of studying interstellar objects. They represent the ultimate frontier of comparative planetology, allowing us to study the products of stellar systems we may never visit directly. Each spectrum we take, each image we capture, each measurement we make is a form of interstellar archaeology, reconstructing the history of distant worlds from the fragments they've sent our way. As 3I Atlas continues its journey away from our Sun, gradually fading from view as it returns to the darkness between the stars, it leaves behind a wealth of data that will keep astronomers busy for years to come. More importantly, it leaves us with a new appreciation for our place in the cosmic community and a deeper understanding of the connections that bind all stellar systems together in the grand dance of galactic evolution. But even as we bid farewell to this ancient traveller, new mysteries await our exploration. The quantum realm, that strange domain where particles exist in multiple states simultaneously and reality itself seems to bend the rules of logic, presents puzzles that make the anomalies of 3I Atlas seem straightforward by comparison. In that invisible world of atoms and subatomic particles, scientists have discovered phenomena so bizarre, so fundamentally challenging to our understanding of existence, that they've sparked decades of debate about the very nature of reality itself. The measurement problem in quantum mechanics suggests that the act of observation might literally create the reality we observe, a possibility so unsettling that even Einstein rejected it with his famous declaration that God does not play dice with the universe. As we watch 3I Atlas fade into the cosmic distance, its ancient light growing dimmer with each passing day, there's a peculiar silence settling over the astronomical community. Not the silence of completion, but the silence of anticipation. You see, when something as extraordinary as this interstellar wanderer graces our solar system with its presence, it doesn't just answer questions, it opens doorways to entirely new realms of inquiry. The data streams are still flowing in from observatories around the world, terabytes of information, captured during those precious months when 3I Atlas was close enough to study in detail. Each spectrum, each image, each measurement represents a breadcrumb trail leading us deeper into the mystery of what lies beyond our cosmic neighbourhood. And as astronomers pore over this treasure trove of information, patterns are beginning to emerge that no one quite expected. Dr. Sarah Chen at the Caltech Optical Observatory described it to me in a way that sent chills down my spine. She said, "It's like we've been listening to a symphony our entire lives, thinking we knew all the instruments in the orchestra. Then suddenly we hear a note that doesn't belong to any instrument we recognise. The question isn't just what made that sound, it's what else might be out there that we haven't heard yet." The carbon dioxide emissions from 3I Atlas aren't just unusual, they're following patterns that seem almost too organised, too structured, to be entirely random. The release rates fluctuate in ways that suggest internal processes we don't yet understand. Some researchers have begun to wonder if the comet's nucleus contains structures, perhaps cavities or channels, that focus and direct the sublimation of volatile materials in ways that create these organised emission patterns. But perhaps most intriguingly, the nickel vapour detected in the comet's coma has been showing spectral signatures that don't quite match what we see in laboratory samples of pure nickel. There are subtle shifts in the emission lines, minute variations that suggest the nickel atoms in 3I Atlas might be bound up in molecular complexes we've never encountered before. It's as if this ancient visitor is teaching us about chemistry that doesn't exist naturally in our solar system. Deep in the archives of the European Southern Observatory, a team of spectroscopists has been conducting analysis so detailed, so painstakingly precise, that it's taken months to process the data from just a few nights of observations. What they're studying are isotope ratios, the relative abundance of different forms of the same element. In the materials streaming from 3I Atlas, isotopes are like fingerprints of cosmic processes. The ratio of different isotopes of carbon, oxygen, and nitrogen in a celestial object can tell us about the temperature, pressure, and radiation environment where those materials formed. Each star system leaves its own isotopic signature in the materials it produces, a kind of stellar DNA that persists for billions of years. The preliminary results from these isotopic studies of 3I Atlas are, in the words of Dr. Maria Gonzalez, the lead researcher, deeply unsettling. The ratios they're finding don't match any known stellar nucleosynthesis processes. It's as if the materials in this comet were forged under conditions that don't exist around any type of star we've catalogued. Consider what this means. We've studied thousands of stars, from young, hot giants to ancient, cool dwarfs. We've observed stellar nurseries where new stars are born and stellar graveyards where old ones die. We've witnessed supernovas, neutron star collisions, and black hole mergers. From all of these observations, we've built a comprehensive understanding of how the elements are created and distributed throughout the galaxy. But the isotope ratios in 3I Atlas suggest nucleosynthesis processes that fall outside this framework. Either this comet formed around a type of star we've never encountered, or its materials have been processed by some mechanism we don't yet understand. The implications ripple outward like waves on a cosmic pond, touching everything we think we know about stellar evolution and galactic chemical enrichment. There's a third possibility that some researchers are hesitant to voice publicly, but it whispers through conference hallways and late-night email exchanges. What if the unusual isotope ratios aren't the result of natural stellar processes at all? What if they represent the signature of artificial nucleosynthesis, the deliberate manipulation of matter by an advanced civilization? It sounds like science fiction, and perhaps it is. But when you're confronted with data that doesn't fit any natural explanation, you have to consider unnatural ones. The isotope ratios in 3I Atlas could be the calling card of a technology so advanced that it can manipulate matter at the nuclear level, creating materials with properties tailored for specific purposes. But let's step back from these speculative possibilities and consider something even more profound. The discovery of 3I Atlas has forced astronomers to confront a reality that's been hiding in plain sight. Our galaxy is not a collection of isolated star systems, but a vast, interconnected network where matter, information, and potentially even life flow between stellar communities across space and time. Think about the implications of this network effect. Every star system produces ejected materials. Comets, asteroids, and planetary fragments accelerated to interstellar velocities by gravitational interactions or stellar evolution. These objects carry with them the chemical signatures, the isotopic fingerprints, and potentially even the biological materials of their home systems. Over the billions of years of galactic history, trillions of these interstellar wanderers have crisscrossed our galaxy, creating a slow-motion exchange of materials that connects every stellar system to every other system. We're not studying isolated islands of matter and energy. We're examining nodes in a vast cosmic web where information flows at the speed of ejected asteroids and comets. This network operates on timescales that dwarf human civilization, but it's been active since the galaxy first formed. The oldest stars, those ancient giants that formed when the universe was young, have been contributing to this interstellar exchange for over 10 billion years. Their ejected materials have had time to travel across significant fractions of the galaxy, seeding other star systems with the chemical products of primordial stellar evolution. When we study 3I Atlas, we're not just learning about one object, or even one star system. We're tapping into this galactic information network, accessing data that's been accumulated and transmitted across vast distances and enormous spans of time. The comet becomes a messenger not just from its birth system, but from the entire galactic community of which it has been a part. The networking effect helps explain some of the puzzling aspects of 3I Atlas. Its unusual chemical composition might not represent the pure products of its original star system, but rather a composite signature created by its interactions with the interstellar medium during its billion-year journey. Cosmic rays, stellar winds, and encounters with other interstellar objects could all have contributed to modifying its chemistry in ways that create the exotic signatures we observe today. As we continue to study 3I Atlas and await the discovery of future interstellar visitors, we're forced to confront a philosophical question that sits at the heart of modern astronomy. What is the relationship between the observer and the observed in a universe where information can travel between star systems? This isn't just an abstract philosophical puzzle. If our galaxy is truly a connected network of matter and information exchange, then every civilization that achieves the ability to study interstellar objects becomes part of that network. We're not passive observers studying distant phenomena. We're active participants in a galactic-scale information system. Consider the trajectory of 3I Atlas as it passes through our solar system. Our observations, our measurements, our very presence as an observing civilization become part of the comet's story. When it eventually approaches another star system billions of years in the future, it will carry with it not just the chemical signatures of its birth world and its interstellar journey, but also the subtle influences of its encounter with our technology. The radio waves from our telescopes reflected off the comet's nucleus will propagate into interstellar space, carrying information about our civilization. The slight warming caused by our infrared observations will alter the comet's sublimation patterns in microscopic but measurable ways. Even the gravitational influence of our spacecraft, infinitesimal though it may be, will contribute to tiny changes in the comet's trajectory. Future civilizations studying 3I Atlas, when it visits their star systems, will find embedded within its structure and chemistry the signatures of every world it has encountered along its journey. We become part of its message, contributors to the information it carries across the galaxy. This perspective transforms our understanding of what it means to be an observing civilization. We're not detached scientists studying specimens in a cosmic laboratory. We're participants in a vast, slow conversation that spans the galaxy and operates across geological timescales. When we detect the exotic chemistry of 3I Atlas, when we map its unusual trajectory, when we puzzle over its anomalous properties, we're not just gathering scientific data, we're receiving messages from other participants in this galactic network. And through our observations, our measurements, our very curiosity about this ancient wanderer, we're composing our own messages to be carried forward to future recipients we will never meet. There's another layer to this cosmic network that some researchers are beginning to explore, though it ventures into territory where science and philosophy become nearly indistinguishable. If matter and information flow between star systems through objects like 3i Atlas, and if consciousness is ultimately a product of information processing, then could this galactic network be transmitting something more than just chemistry and physics? The question isn't whether 3i Atlas is conscious. That seems highly unlikely for a ball of ice and rock, regardless of how exotic its composition. But could it be carrying the products of consciousness? The information patterns created by thinking beings in other star systems? Complex organic molecules have been detected in interstellar space, including amino acids and even simple peptides. These building blocks of life can survive the harsh conditions of the interstellar medium, protected by ice or incorporated into dust grains. Objects like 3i Atlas, with their billions of years of travel time and their ability to collect materials from multiple sources, could potentially serve as repositories for organic information that originated in living systems. This isn't idle speculation. Panspermia, the idea that life spreads between worlds through natural processes, has been seriously considered by scientists for decades. If microorganisms can survive interstellar travel embedded in comets and asteroids, then the products of more complex biological processes might also make the journey. But we can take this idea even further. If advanced civilizations exist in our galaxy, and if they've learned to encode information in durable physical substrates, then objects like 3i Atlas could be carrying libraries, archives, even the preserved patterns of individual consciousnesses across the vast distances between stars. The unusual isotope ratios in 3i Atlas, the exotic molecular chemistry, the organized emission patterns, what if these aren't just the products of unknown stellar processes, but information storage systems created by an advanced civilization? What if we're not just studying a comet, but attempting to read a message written in the language of atomic and molecular engineering? This possibility, remote though it may be, adds another dimension to our study of interstellar objects. Every spectrum we take, every image we capture, every measurement we make might be revealing not just the physical properties of these ancient wanderers, but the thoughts and dreams of beings who lived around other stars billions of years ago. As 3i Atlas continues its journey away from our sun, becoming a fading point of light against the star-filled background, it serves as more than just a scientific curiosity. It becomes a mirror, reflecting back to us questions about our own place in the cosmic order and our relationship with deep time. The comet has existed for billions of years, potentially longer than complex life has existed on Earth. During its journey through interstellar space, entire geological epochs have passed on our world. The Cambrian explosion, the rise and fall of the dinosaurs, the evolution of mammals, the emergence of human consciousness. All of these pivotal moments in Earth's history have occurred during the time that 3i Atlas has been wandering between the stars. Yet from the perspective of this ancient traveller, these events are merely brief fluctuations in the cosmic background, momentary eddies in the vast river of time that flows through the galaxy. The comet's existence spans timescales that reduce all of human history to a single heartbeat, all of recorded civilization to a fleeting thought. This perspective is both humbling and liberating. Humbling because it reminds us of our infinitesimal place in the grand scheme of cosmic evolution. But liberating because it suggests that we're part of something much larger and more enduring than our immediate concerns and temporal anxieties. The network of interstellar exchange that 3R Atlas represents operates on these vast timescales, connecting not just different places in the galaxy, but different eras of cosmic history. When we study this ancient visitor, we're not just learning about contemporary conditions in other star systems, we're reaching back through time to touch the early galaxy, to sample materials that formed when the universe was fundamentally different from what we see today. In a very real sense, 3I Atlas is a time machine, carrying forward the chemistry and physics of ancient stellar environments and delivering them to our doorstep for analysis. Through its exotic composition and unusual properties, we can study processes that operated billions of years ago around stars that have long since died and been recycled into new generations of stellar offspring. The study of 3I Atlas is already beginning to influence other areas of astronomy and planetary science in ways that weren't initially obvious. The techniques developed to analyze its unusual chemistry are being applied to the study of exoplanet atmospheres, helping astronomers identify and characterize the chemical compositions of worlds orbiting other stars. The orbital dynamics calculations that revealed its interstellar origin are informing models of planetary system evolution, providing new insights into how gravitational interactions can scatter objects across galactic distances. The isotope analysis methods being used to decode its chemical fingerprints are being adapted for studying meteorites and lunar samples, offering new ways to understand the early history of our own solar system. But perhaps most significantly, the discovery of 3I Atlas has changed how astronomers think about the prevalence and importance of interstellar objects. What was once considered an exotic rarity is now recognized as a fundamental component of galactic evolution, a mechanism for transporting matter, information, and potentially even life between stellar systems. This shift in perspective is driving new observational campaigns, new theoretical models, and new mission concepts. The upcoming Vera Rubin Observatory will dedicate significant observing time to discovering and characterizing interstellar objects. Space agencies are considering dedicated missions to intercept and study these visitors in detail. Theoretical astronomers are developing new models of galactic chemical evolution that account for the role of interstellar transport. The ripple effects extend beyond astronomy into related fields. Astrobiologists are reconsidering the mechanisms by which life might spread between worlds, taking into account the possibility of interstellar panspermia mediated by objects like 3I Atlas. Planetary scientists are developing new models of atmospheric evolution that consider the input of interstellar materials. Even philosophers and ethicists are grappling with the implications of living in a galaxy where information and potentially consciousness can be transmitted between civilizations across vast spans of space and time. The challenges posed by studying 3I Atlas are driving innovations in astronomical technology that will benefit science for decades to come. The need to detect faint spectral lines from exotic molecules has pushed the development of more sensitive spectrographs. The requirement to track rapidly moving objects has led to improvements in telescope pointing and tracking systems. The demand for rapid follow-up observations has catalyzed advances in automated survey systems and real-time data processing. But perhaps most importantly, the study of interstellar objects is driving the development of new spacecraft technologies. The high velocities and unpredictable arrival times of these visitors require spacecraft that can be launched quickly, accelerate rapidly, and operate autonomously far from Earth. These technological developments have applications far beyond interstellar object research. The same propulsion systems that might be used to intercept a fast-moving comet could enable rapid missions to the outer planets. The autonomous navigation systems required for interstellar object encounters could be adapted for asteroid mining operations. The advanced spectrometers needed to analyze exotic chemistry could revolutionize the search for life on Mars and the moons of the outer planets. In this way, 3i Atlas becomes more than just a scientific curiosity. It becomes a technological catalyst, driving innovations that expand our capabilities throughout the solar system and beyond. The comet challenges us not just intellectually, but technologically, forcing us to develop new tools and techniques that will serve us well as we expand our presence into the cosmos. The legacy of 3i Atlas will be measured not just in the papers published about its unusual properties, but in the technological advances it inspired and the new capabilities it helped create. Long after the comet has faded from view, the tools developed to study it will continue to serve science, opening new windows into the cosmos and enabling discoveries we can't yet imagine. As our journey through the mystery of 3i Atlas draws toward its conclusion, it's worth reflecting on how many questions this single object has raised. We began with a seemingly straightforward discovery, an interstellar comet passing through our solar system. But each answer we've uncovered has revealed new layers of complexity, new puzzles to solve, new mysteries to explore. The perfect alignment of its trajectory with our planetary plane remains unexplained. The unusual chemistry dominated by carbon dioxide, rather than water, challenges our understanding of comet formation. The exotic isotope ratios suggest nucleosynthesis processes we don't recognize. The organized emission patterns hint at internal structures we can't yet resolve. But perhaps the most profound question raised by 3i Atlas isn't about the comet itself, but about us. What does it mean to be an observing civilization in a galaxy where information flows between star systems through physical messengers like this ancient wanderer? How do we fit into the vast network of matter and energy exchange that connects all stellar communities across space and time? These questions don't have simple answers. They require us to expand our thinking beyond the boundaries of our solar system, beyond the timescales of human experience, beyond the comfortable assumption that we're isolated observers studying distant phenomena. They challenge us to see ourselves as participants in a cosmic community that operates on scales we're only beginning to comprehend. The study of 3i Atlas has shown us that the universe is more connected, more dynamic, and more mysterious than we previously imagined. It has revealed a galaxy where matter carries information across vast distances, where the products of stellar evolution mix and mingle through interstellar exchange, where the chemistry of one star system can influence the composition of worlds orbiting other stars. As we continue to observe this remarkable visitor until it fades beyond the reach of our telescopes, as we analyze the data it has provided and prepare for the arrival of future interstellar objects, we carry with us a new appreciation for our place in the cosmic order. We are not alone, not isolated, not separate from the grand dance of galactic evolution. We are part of it, participants in a story that began billions of years ago and will continue long after our sun has died, and our Earth has been recycled into new worlds orbiting younger stars. And so, as 3i Atlas fades into the cosmic distance, its ancient journey continuing toward destinations we can only imagine, we're left with a profound sense of connection to the deep history of our galaxy. This remarkable object has served as our guide into realms of space and time that dwarf human experience, yet somehow make us feel more at home in the universe rather than less. The comet will continue its eternal voyage, carrying with it the subtle influences of its encounter with our civilization. The radio waves we've bounced off its surface, the slight warming from our infrared observations, the infinitesimal gravitational perturbations from our spacecraft, all of these will accompany it as it travels toward future star systems and future civilizations that may study it billions of years hence. In that sense, 3i Atlas becomes a messenger not just from its ancient birthplace, but from us. Our curiosity, our wonder, our relentless drive to understand the cosmos around us. These too become part of its cargo as it continues its journey through the galaxy. Future beings studying this object will find embedded within its structure and chemistry the signatures of our presence, our technology, our moment of contact with this wanderer from the deep. There's something beautifully poetic about this exchange. We receive a message from the ancient galaxy encoded in exotic chemistry and unusual physics. In return, we send forward our own message, written in the language of electromagnetic radiation and gravitational influence, to be delivered to recipients we will never meet around stars that may not yet exist. This is how the galaxy learns about itself, through the slow exchange of matter and information carried by objects like 3i Atlas across the vast emptiness between the stars. Each encounter, each measurement, each moment of wonder becomes part of a vast conversation that spans space and time on scales that challenge human comprehension. As we bid farewell to this ancient traveller and return our attention to the countless mysteries that surround us, we carry with us a new understanding of our place in the cosmic community. We are not observers standing apart from the universe we study. We are participants in its evolution, contributors to its story, partners in its endless dance of discovery and transformation. The journey of 3i Atlas through our solar system reminds us that the universe is not just vast and ancient, but also intimate and immediate. The atoms streaming from this interstellar comet, the photons carrying information about its exotic chemistry, the gravitational influences shaping its trajectory, all of these connect us directly to processes that began billions of years ago around stars whose light has long since faded. In studying this remarkable object, we've touched the deep history of our galaxy and added our own chapter to its ongoing story. And as 3i Atlas continues its eternal journey, it carries forward not just the chemistry of its ancient birthplace, but also the signatures of our curiosity, our wonder, and our unending quest to understand the cosmos we call home. But even as we contemplate these vast scales of space and time, these ancient connections between distant worlds and civilizations, there exists another realm where the very nature of reality becomes even more mysterious and unsettling. In the quantum world that underlies all of existence, scientists have discovered phenomena so bizarre, so fundamentally challenging to our understanding of what it means for something to exist, that they've sparked decades of debate about whether our universe is even real. The measurement problem in quantum mechanics suggests that reality itself might be far more fragile and observer-dependent than we ever imagined. Particles that exist in multiple states simultaneously until observed, information that travels faster than light, and the possibility that consciousness itself plays a fundamental role in shaping the physical world. These are the mysteries that keep physicists awake at night, wondering if everything we think we know about existence might be nothing more than an elaborate illusion. That's exactly what we'll be exploring next time, in the quantum paradox, terrifying scientists, and they can't explain it. Thank you for joining me on this journey to the edges of our solar system and the boundaries of our understanding. Until next time, keep looking up, keep questioning, and remember that in a universe as vast and connected as ours, every moment of curiosity becomes part of an eternal conversation between worlds. There's something profoundly melancholic about watching an ancient visitor prepare to leave. As the final observations of 3i Atlas trickle in from observatories around the world, each data point feels precious, irreplaceable. We're witnessing the end of humanity's first extended encounter with a messenger from the deep past, and there's no guarantee we'll ever see its like again in our lifetimes. The comet has dimmed considerably since its discovery, its coma gradually dissipating as it moves away from the sun's warming influence. But even in this fading light, it continues to surprise us. Recent spectroscopic observations have detected subtle changes in its emission patterns, as if the comet is slowly shutting down its exotic chemistry, returning to the dormant state it maintained during its billion-year journey through interstellar space. Dr. Elena Rossi at the La Palma Observatory described the final observations to me with a poignancy that's rare in scientific discourse. It's like watching someone you've just met pack their bags and prepare for a journey you know they'll never return from, she said. We've learned so much about this ancient traveller in just a few short months, but it feels like we've barely scratched the surface of its mysteries. The infrared emissions that once blazed with the signatures of carbon dioxide and exotic molecules have begun to fade. The nickel and cyanide vapours that puzzled astronomers with their organised patterns are dissipating into the solar wind. Even that mysterious sunward-pointing tail has started to diminish as the comet's nucleus cools and its exotic material ejection processes slow to a whisper. Yet in this gradual silencing, there's something that speaks to the deeper rhythms of cosmic time. 3i Atlas is not dying. It's simply returning to the patient state of hibernation that has characterized most of its existence. The brief flare of activity we witnessed as it passed through our inner solar system was an anomaly, a momentary awakening in an otherwise eternal sleep. As 3i Atlas retreats toward the outer darkness, astronomers around the world are beginning the painstaking process of analysing the vast archive of data collected during its visit. Thousands of spectra, tens of thousands of images, millions of individual measurements, all waiting to be processed, correlated, and interpreted. This data archive represents something unprecedented in the history of astronomy. Never before have we been able to study an interstellar object with such detail and precision. Every wavelength of light from radio waves to gamma rays has been captured and catalogued. The chemical composition of its coma has been mapped with unprecedented resolution. The subtle variations in its emission patterns have been tracked with exquisite temporal precision. But raw data is just the beginning of the story. The real discoveries will emerge as researchers begin to find patterns and correlations hidden within this vast data set. Machine learning algorithms are already being deployed to search for subtle periodicities in the emission patterns, signs of internal structure that might explain the comet's unusual behaviour. Dr. Kenji Nakamura at the Subaru Observatory has been developing new analysis techniques specifically for processing the 3i Atlas data. We're not just looking for what we expected to find, he explained to me. We're searching for signals we didn't even know to look for. Patterns that might reveal entirely new aspects of interstellar object physics. The isotope analysis alone will take years to complete. Each spectral line must be carefully measured and compared to laboratory standards. The ratios of different isotopes must be calculated with extraordinary precision to detect the subtle variations that encode information about the comet's origin. The process is painstaking, but the potential rewards are enormous. If the preliminary results hold up under detailed scrutiny, 3I Atlas will have provided us with the first direct evidence of nucleosynthesis processes that don't occur around any known type of star. This would force a fundamental revision of our understanding of stellar evolution and galactic chemical enrichment, opening new chapters in the textbooks of astrophysics. The challenges of studying 3I Atlas have pushed astronomical technology to its limits and beyond. The need to extract maximum information from a rapidly fading target has driven innovations in detector sensitivity, data processing algorithms, and observational techniques that will benefit astronomy for decades to come. New spectrograph designs optimized for detecting faint emission lines from exotic molecules are already being incorporated into the next generation of ground-based telescopes. The rapid response observing protocols developed to coordinate observations of the comet are being adapted for studying other transient phenomena like supernovae and gamma-ray bursts. But perhaps most significantly, the study of 3I Atlas has demonstrated the power of global collaboration in astronomy. When this ancient visitor was discovered, observatories around the world immediately began working together, sharing data, coordinating observations, and pooling expertise to maximize the scientific return from this once-in-a-lifetime opportunity. This collaborative model is becoming the new standard for studying rare and rapidly evolving astronomical phenomena. The networks of trust and communication established during the 3I Atlas campaign will continue to serve the astronomical community as we face future challenges and opportunities. The space agencies have also taken notice. The European Space Agency has already begun preliminary studies for a dedicated interstellar object interceptor mission designed to launch rapidly when the next visitor is discovered. NASA is considering modifications to existing spacecraft that could enable opportunistic encounters with interstellar objects passing through the outer solar system. These technological developments represent more than just scientific progress. They're preparing humanity for our eventual expansion beyond the solar system. The same technologies that allow us to study interstellar visitors will one day enable us to become interstellar travelers ourselves. As we watch 3I Atlas fade into the cosmic background, its journey forces us to confront questions that extend far beyond astronomy. What does it mean to be conscious observers in a universe where ancient messengers regularly cross the vast emptiness between stars? How do we process the knowledge that we've touched, however briefly, materials older than our entire solar system? The comet's passage through our neighbourhood serves as a profound meditation on the nature of time and connection. For billions of years, this object has been travelling through space, carrying within its frozen nucleus the chemical signatures of processes that occurred when the galaxy was young. Its arrival at our solar system represents a convergence of timelines that spans most of the history of the universe. Yet for all its ancient majesty, 3I Atlas has also reminded us of our own agency in the cosmic story. Through our observations, our measurements, our very attention to this wandering messenger, we've become part of its narrative. The photons we've bounced off its surface, the slight gravitational influences of our spacecraft, the electromagnetic signatures of our technology, all of these will accompany the comet as it continues its eternal journey. In a very real sense, we've achieved a form of immortality through our encounter with 3I Atlas. Long after our civilization has passed into history, long after our sun has exhausted its fuel and our Earth has been consumed by stellar evolution, this ancient traveller will carry forward the subtle signatures of our presence. Future civilizations studying the comet around distant stars will find embedded within its structure the faint echoes of our curiosity and wonder. This perspective transforms how we think about our place in the cosmic community. We're not isolated observers studying distant phenomena. We're active participants in a vast conversation that spans the galaxy and operates across geological timescales. Every observation we make, every question we ask, every moment of wonder we experience becomes part of the information flowing through this cosmic network. As 3I Atlas continues its journey toward the heliopause and beyond, it will gradually return to the profound silence that has characterized most of its existence. No more solar radiation to sublimate its exotic ices. No more planetary gravitational fields to perturb its trajectory. No more curious astronomers tracking its every movement and analysing its every emission. The comet will become once again a dark, cold wanderer drifting through the near-perfect vacuum of interstellar space. Its exotic chemistry will freeze into inactivity. Its mysterious internal structures will remain hidden beneath layers of cosmic ray-processed crust. The organised emission patterns that so puzzled our instruments will fall silent, waiting for the warmth of another star to reawaken them. But this silence is not emptiness. It's the silence of patience, of endurance, of materials that have survived journeys beyond human comprehension. In that darkness between the stars, 3I Atlas will carry forward not just the chemical signatures of its ancient birthplace, but also the subtle influences of its encounter with our civilization. The interstellar medium through which it travels is not the empty void we once imagined. It's filled with gas and dust, magnetic fields and cosmic rays, the detritus of stellar evolution, and the raw materials for future star formation. 3I Atlas will interact with this medium in ways both subtle and profound, gradually exchanging materials and information with the galaxy at large. Cosmic rays will continue to bombard its surface, slowly altering its chemistry and creating new isotopic signatures. Encounters with interstellar dust clouds will add new materials to its collection. The weak gravitational fields of passing stars will subtly adjust its trajectory, sending it on paths that might eventually lead to encounters we can't predict or imagine. The discovery and study of 3I Atlas has fundamentally changed how astronomers think about the population of interstellar objects in our galaxy. What was once considered an exotic rarity is now recognized as a fundamental component of galactic evolution, a vast population of wanderers carrying materials and information between stellar systems. Current estimates suggest that thousands of interstellar objects may be passing through our solar system at any given time, most too small or too dark to detect with current technology. The Vera Rubin Observatory, with its unprecedented surveying power, may discover dozens or even hundreds of these visitors in the coming decade. Each new discovery will add another piece to the puzzle of galactic chemical evolution. Some may be similar to 3I Atlas, carbon-rich wanderers from the ancient galaxy carrying exotic isotope signatures. Others might be water-rich objects, more similar to the comets of our own solar system, ejected from younger stellar communities. Still others might represent entirely new categories of interstellar objects we haven't yet imagined. The diversity we're beginning to discover among interstellar objects reflects a diversity of environments where they formed. Different types of stars, different stellar masses, different metallicities, different orbital dynamics. All of these factors influence the composition and properties of the objects ejected from planetary systems. As we build up a statistical sample of interstellar visitors, we'll begin to construct a kind of census of galactic chemical evolution. The isotope ratios, molecular compositions, and physical properties of these objects will tell us about the history of star formation, the evolution of planetary systems, and the processes that drive chemical enrichment throughout the galaxy. Looking ahead to the deep future, the study of objects like 3I Atlas offers a glimpse into humanity's potential role as participants in the galactic community. As our technology advances and our presence in space expands, we may one day become contributors to the interstellar object population ourselves. Our spacecraft, launched toward other star systems, will become the 3I Atlas of the future, artificial wanderers carrying the signatures of our civilization across the vast distances between stars. The Voyager probes, already in interstellar space, represent our first tentative steps toward becoming a spacefaring civilization that contributes to the galaxy's information network. Future generations might deliberately design interstellar messengers, objects crafted to carry our knowledge, our culture, our very essence to civilizations around distant stars. These artificial comets could be encoded with information about our biology, our history, our understanding of the universe, creating a kind of interstellar library system that operates on cosmic timescales. The techniques we've developed to study 3I Atlas, the spectroscopic analysis, the isotope measurements, the orbital dynamics calculations, will serve us well when we encounter our own interstellar messengers around other stars. We're learning the language of interstellar communication, developing the tools needed to read the messages carried by these ancient wanderers. In a very real sense, the study of 3I Atlas is preparing us for our eventual emergence as a galactic civilization. We're learning to think on cosmic timescales, to communicate across interstellar distances, to participate in the vast conversation that connects all thinking beings in our galaxy. As 3I Atlas fades beyond the reach of our most powerful telescopes, becoming once again a dark point of matter drifting through the cosmos, we're left with a profound sense of having witnessed something extraordinary. This ancient messenger has shown us that our galaxy is not a collection of isolated star systems, but a vast interconnected web where matter, energy, and information flow freely across space and time. The comet's visit has been briefed by cosmic standards, just a few months of close observation before it returned to the darkness between the stars. But in that brief time, it has fundamentally changed our understanding of our place in the universe. We've learned that we're part of a community that extends far beyond our solar system, connected to distant worlds and ancient processes through the medium of wandering messengers like 3I Atlas. The questions raised by this remarkable object will occupy scientists for decades to come. The data collected during its passage will be analysed and reanalyzed, revealing new insights and raising new mysteries. The technological innovations driven by the challenges of studying it will enable discoveries we can't yet imagine. But perhaps most importantly, 3i Atlas has reminded us of the power of curiosity and wonder to connect us with the deepest mysteries of existence. In studying this ancient wanderer, we've touched the primordial galaxy, sampled materials from the dawn of time, and glimpsed the vast scales on which the universe operates. The journey of 3i Atlas through our solar system represents more than just a scientific opportunity. It's a profound meditation on time, space, and our place in the cosmic order. As we bid farewell to this ancient traveller and await the arrival of future interstellar visitors, we carry with us a new appreciation for the connections that bind us to the larger universe. Standing at the threshold between the known and the unknown, between the familiar confines of our solar system and the vast mysteries of interstellar space, we find ourselves changed by our encounter with 3i Atlas. This ancient messenger has served as more than just a scientific specimen. It has been our guide into realms of existence that operate on scales almost beyond human comprehension. The exotic chemistry flowing from its nucleus, the impossible trajectory that brought it to our doorstep, the organised patterns in its emissions that hint at structures we don't yet understand. All of these phenomena have forced us to expand our conception of what's possible in the universe. We've been reminded that reality is far stranger, far more interconnected, and far more mysterious than our everyday experience suggests. As the comet continues its eternal journey toward destinations we can only imagine, it carries with it the subtle signatures of our civilization. Our radio telescopes have painted it with electromagnetic radiation that will propagate into interstellar space. Our infrared observations have added microscopic amounts of heat to its ancient surface. Our very attention has become part of its story. In this exchange of information and influence, we glimpse something profound about the nature of consciousness and its role in the cosmic story. We are not passive observers of the universe. We are active participants in its evolution, contributors to the vast conversation that flows between worlds and civilizations across the galaxy. The study of 3i Atlas has shown us that the boundary between observer and observed is far more fluid than we once believed. In measuring the comet's properties, we have altered them. In studying its behaviour, we have influenced it. In seeking to understand this ancient messenger, we've become part of the message it carries forward to future encounters around distant stars. This realization opens up entirely new ways of thinking about science, consciousness, and our relationship with the universe we inhabit. If the act of observation can influence what we observe, if consciousness plays an active role in shaping reality, then perhaps the universe is far more participatory, far more alive than we ever dared imagine. But these questions about the role of consciousness in shaping reality are not unique to the study of interstellar objects. They echo through every corner of modern physics, from the quantum realm, where particles exist in multiple states until observed, to the cosmological scales where the very act of measurement seems to influence the structure of space-time itself. Indeed, there exists a domain of physics where these questions become so profound, so fundamentally unsettling, that they challenge our most basic assumptions about the nature of existence. In the quantum world, scientists have discovered phenomena so bizarre that many refuse to accept their implications, preferring to retreat into mathematical formalism rather than confront the possibility that reality itself might be far more fragile and observer-dependent than we ever imagined. As we contemplate the fading light of 3i Atlas and the mysteries it has revealed about our connected universe, we find ourselves standing at the edge of an even deeper mystery, one that strikes at the very heart of what it means for something to exist. The quantum measurement problem suggests that consciousness itself might play a fundamental role in determining the structure of reality, a possibility so unsettling that it has divided the physics community for nearly a century. That's exactly what we talked about last time. In The Quantum Paradox Terrifying Scientists, and They Can't Explain It. Thank you for joining me on this journey to the edges of our solar system and the boundaries of our understanding. Until we meet again in the quantum realm, keep looking up, keep questioning, and remember that in a universe as mysterious and interconnected as ours, every moment of wonder becomes part of an eternal conversation between consciousness and cosmos. But there's something else about 3i Atlas that haunts the quiet corners of scientific discourse, something that researchers whisper about in observatory cafeterias and late-night email exchanges. It's the uncomfortable realization that this ancient wanderer has forced us to confront the limits of our own existence, the brevity of our moment in cosmic history. So here we stand, having journeyed alongside this ancient messenger from the depths of space and time, forever changed by the encounter. 3i Atlas has shown us that our galaxy is not a collection of isolated islands, but a vast network where matter, information, and perhaps even consciousness flow between worlds across billions of years. Its exotic chemistry, impossible trajectory, and mysterious behaviour have reminded us that the universe still holds secrets that challenge everything we think we know. As this remarkable visitor fades into the cosmic darkness, it carries forward the subtle signatures of our curiosity, our wonder, our brief moment of connection with the eternal dance of galactic evolution. We are not merely observers of this cosmic story, we are participants in it, contributories to a conversation that spans the stars and operates on timescales that dwarf human civilization. Until next time, keep questioning, keep wondering, and remember that in a universe this strange and interconnected, the most profound mysteries often arrive unannounced at our cosmic doorstep.